Hello, in this video I'm going to be going over Le Chatelier's principle. What is Le Chatelier's principle? It states that when a system at equilibrium is subjected to a stress, the system will shift its equilibrium point in order to relieve that stress. So how I look at equilibrium is kind of like a teeter-totter, and what's happening is it wants to be level, equal. But when you put someone heavier on one side, it's going to sink. And so the equilibrium is going to then either turn into reactants or products to stabilize and come back to equilibrium. And when something heavier is put on that teeter-totter, that's called a stress. And you can have, there's four main stresses that we look at. There's concentration, there's pressure, there's volume, and there's temperature. And we're going to go over all four of those. Alright, so doing an example problem, we have N2 plus 3H2 reacts to form 2NH3 and plus 22.0 kilocalories. This energy in this thermonuclear equation is on the product side, which would indicate it is exothermic, a negative delta H. And I think of energy the same way that I think of products and reactants when doing equilibrium with Le Chatelier's principle. Alright, so for this first one, it's already done for you, but just going over it, it says if we add N2. So we are increasing our amount of N2. Alright, so if we're increasing N2, this teeter-totter is unbalanced, so it looks like this. We have more reactants than we do products, so the equilibrium is going to shift to the right to balance this out so that we have just as many products as we do reactants according to the equilibrium constant. Alright, so the stress is being added to N2, so we omit that, but H2 is going to decrease because more of these reactants are going to react to form product, therefore H2 decreases, and NH3 is going to increase because more products are going to be formed. Looking at K, what is K? K is the equilibrium constant. Remember, the equilibrium constant is going to be NH3 to the power of 2, coefficient becomes the power, divided by N2 concentration times H2 concentration to the power of 3. So whenever we change our concentration, we add reactants or products, it's not going to change our equilibrium constant. What will change it is if you change the temperature or the pressure. That will definitely change it, and we'll get to that in a little bit. Alright, so adding H2. If we add H2, we have the same kind of thing happening. We have more reactants, so it's going to shift to the right. I'm just going to put an arrow right there, and more products are going to be formed. Therefore, we would say that products are favored. Alright, and N2, if we add more reactants, it's going to basically go down. More reactants are going to react to form a product, so N2 is going to decrease, whereas NH3 increases. NK is going to remain the same. Alright. Next one, if we add NH3, adding NH3, that's this product, this product right here, we're adding it. So really what's happening is we have a lot of product and not as much reactant. So the equilibrium is going to shift to the left to balance this out so that this can go down and this can go up. So when that happens, this N2 is going to increase, that H2 is going to increase, that NH3 is where the stress is happening, and our K, because our concentration is the only thing that's changing, we're just going to write the same. Doesn't change. Alright, removing N2. So if we remove N2, essentially what we're doing is we're decreasing the amount of reactants, therefore equilibrium is going to shift to the left to reform those reactants that are now lost. Equilibrium shifts to the left. Alright, and then H2, if we're shifting to the left, that's going to increase, and our NH3 is going to decrease. Kc is going to be the same. I'm just going to zoom out so we can see this better. We remove H2. Same type of deal is happening. We're removing this, so we have less reactants. Less reactants than our products. It's going to shift to the left. Alright, and N2 is a reactant that's going to increase. NH3 is our product that's going to decrease. And equilibrium constant is the same. Removing NH3, so that's going to look like this picture. We're getting less NH3, so we have more reactants. It's going to shift to the right, which means our N2 is going to decrease, our H2 is going to decrease, and our K is going to remain the same because we're just talking about adding or removing, which is just changing the concentration. It doesn't affect Kc. Next, increased temperature. This is where it gets a little tricky, but not too bad. We're going to increase this temperature. And what you do is you look at where the energy is on this equation. Here it's on the product side. So what I do is I just treat the energy like a product. So if I'm increasing temperature, I'm adding energy to wherever the energy is located. In this case, it's on the product side. So it's going to look like this picture. I have more product or energy than I do reactant. So it's going to shift to the left for number 7, which means my two reactants are going to increase and my product is going to decrease. Alright, so now I have to deal with my K. What I have here is my equilibrium constant. We said that my product is going to decrease, so it's going to get smaller, so we have a small number on top. And our reactants are going to increase, so this is a big number. So I have a smaller numerator and a bigger denominator. Whenever you have a situation like that, you're going to get an overall smaller answer. So our Kc is going to decrease under those conditions. Doing another one. We have decreased temperature. So in this one, our energy is on this side. We're decreasing temperature, so we're decreasing the products basically, because energy is on the product side. So it's going to look like this. Smaller product, bigger reactant. We're going to shift right to the right. And our N2 then is going to decrease. Our H2 is going to decrease. And our NH3 is going to increase. So then looking at our Kc, or equilibrium constant, we're going to have a big number on top, and on the bottom it's going to be a smaller number. So big number divided by a smaller number just really compounds it. In both directions you're going bigger. Alright, almost there. Two more. We got increased pressure. So pressure is unique. In this case you have to look at how many molecules you have on each side of the arrow. So here we have 1 N2 and 3 H2. 3 plus 1 is 4. Let's put a little 4 right there. And here we have 2 NH3, and that's the only real molecules that we have, 2. So we have more molecules on the reactant side. In that case, pressure is going to have a greater stress on the reactant side. And when you have increased pressure, you have decreased volume. So all of those molecules are condensed together. And since you have 4 molecules on the reactant side, which is more than what's on the product side, those molecules are going to move around and collide more, therefore reacting for more product. So the equilibrium is going to shift to the product, or favor the products, go to the right, which means our reactants decrease, our product increases, and if our product increases, reactants decrease, our Kc is going to increase again, just like number 8. Number 10, if we decrease pressure, this is going to have the opposite effect. So when pressure is lower, it's going to favor the side that has more molecules. Basically the opposite of when pressure increases. So it's going to favor the reactants, the side that has more molecules, which means our reactant 1, reactant 2 increase, our products decrease, and then our equilibrium constant is going to decrease. So that's just a few examples. It's a conceptual idea, and it's tricky. It's just one of those things that you need to practice a little. And there are 2 sides to this worksheet. If you do have questions, you can always come and ask me during class or during lunch or after school. Hope you enjoyed.